Inversion. Our objectives here are to verify inverse functions. We'll determine the domain and range of an inverse function and restrict the domain of a function to make it one-to-one. Find or evaluate the inverse of a function and use the graph of a one-to-one function to graph its inverse function on the same axes. For a function to have an inverse that is also a function, the original function needs to be a one-to-one function. If you need, you can see the functions lesson for a full review. As just a quick review of this concept, we have here a function in table form. Is it a one-to-one function? We can see that every y is unique. We don't have repeats in any of our output values, and so this is a one-to-one function. You will not have different x's with the same y. Now, an inverse function is a function for which the input of the original function becomes the output of the inverse function, and the output of the original function becomes the input of the inverse function. In this schematic diagram, A is put into the f function and its output is b. Now b is put into the g function and its output is a. F and g here are inverses. Notice that this means that the domain of f is the same as the range of g, and the range of f is the same as the domain of g. Knowing this information, let's find the table for the inverse function f inverse of x. So, our notation, f inverse of x, and it has its inputs. We know that the input for the f function becomes the output of the inverse function, and the output of the original function becomes the input of the inverse function. In other words, each of these points are just switched. The x becomes the y becomes the x. Now let's look at a story example. If you were to walk into a room and sit down, how would you undo this activity? You would stand up and walk out of the room, right? To find the inverse of a function, you must do the inverse of each operation and in the opposite order that each operation was performed. Our first activity was to walk into a room. Second activity was to sit down. The inverse of sitting down is to stand up, and the inverse of walking into a room is walking out of the room. So we've undone the original function using the inverse idea. Now here's a formula example for f of x equals 3x plus 1. The way the original function works is that we have an input, we multiply it by 3, giving us 3x, then we add 1, and we have this output of 3x plus 1. Now the inverse goes in the other direction. We start with some output from the other function. We subtract 1 instead of adding 1. That gives us y minus 1. And then we divide by 3 instead of multiplying by 3. So we have the result of y minus 1 over 3. To be careful, we use a particular notation for y when we're talking about an inverse. The inverse of the f of x function is denoted by the notation f inverse of x. So our original function was f of x equals 3x plus 1, and f inverse of x was x minus 1 over 3. Just a note, in the notation, this f to the negative 1x, the negative 1 is not an exponent. In the context of functions, we're saying that that is an inverse. Assume this function f of x is a one-to-one function. If f of 3 equals 7, find f inverse of 7. We know that this is the input for the f function and this is the output. We know with inverses, this output that we had before is now the input, which means that the output of the inverse function is the input of the original function. Same with this one. If we have f inverse of negative 2 equals 9, what is f of 9? Well, the original f function is the inverse to f inverse. So f of 9 is going to be negative 2. Now in general, f of g of x and g of f of x are not equal. But when they are inverses. Given a function f of x, we can verify whether some other function g of x is the inverse of f of x by checking whether g of f of x equals x and f of g of x equals x are true. Here, verify that f and g are inverses of each other. So we do this by taking f of g of x. This is f of the cube root of x minus 1. And the f function says that we're going to take the input of cube root x minus 1 plus 1 and then cube that. When I simplify the inside, I have the cube root of x. That is still all cubed, and I end up with an x. So far, so good. Now I'm going to take g of f of x. G of f of x is x plus 1 cubed. G of x plus 1 cubed is going to be the cube root of x plus 1 cubed minus 1. The cube root of x plus 1 cubed is just x plus 1, and I still have this minus 1 hanging around, and this is x. Therefore, f and g are inverses. Here's a graphical example. F of x is graphed here. Let's use the graph of f of x to sketch the graph of f inverse of x on the same plane. Well, I kind of see three different parts here. I'd like to go ahead and graph the inverse of those three different parts so that I don't lose track of where I am on the graph. Let's say for this piece right here, I'm getting ready to find the inverse. So for this piece, I have a couple of points I can identify. I have negative 5, negative 4. For the inverse, that's going to be negative 4, negative 5. And this point here, I have a negative 7, negative 10. For the inverse, that'll be a negative 10, negative 7. Okay, now this is just part of a line, so I just need those 2 points in order to graph. The negative 4, negative 5 will end up here. Negative 10, negative 7 ends up here. And I can draw my nice line between them. Okay, for that middle curved piece, you might need to do a little bit more so we can get an idea of what the curve looks like for the inverse function. But again, I have the point -5, -4. I'll go ahead and switch that around. Remember, the x's and y's exchange places. I have, let's say, a 0, -2.8. So we'll say a -2.80. Let's say we have the point 2, 4. So for the inverse, it'll be the point 4, 2. When I graph those, should be connecting there. And a -2.80 is right there, and 4, 2. So you can see the curvature here. And if you don't have a good idea yet of what that looks like, you can always add some more points in there. Get it as smooth as you can. There we are. And our last piece, we're starting off at 2, 4, which becomes 4, 2. That makes sense. And then maybe another point is the point 10, 7. Well, that becomes the point 7, 10 for the inverse. Again, that's just part of a straight line. I just need these 2 points in order to graph it. So 7, 10, and there's my graph. Quite an interesting looking graph. In this example, I'll show you how to work through starting with a function and getting to the inverse function quite directly. First, we have the function f of x equals 1/5 x plus 3. Let's change the f of x notation to just y equals notation. So I'll have y equals 1/5 x plus 3. Now switch x and y. Quite literally, we are taking, anytime we see a y, and put an x instead. Every time we see an x, we put a y instead. Now we want to solve that new equation that we have for y. So my idea is that I want to isolate first the term that has the y in it, the 1/5 the y. I'm going to subtract 3 from both sides. And to get rid of the 1/5 that's in front of the y, I need to multiply both sides by 5. So it'll be 5x minus 15 equals y. Again, we're not finished here, because up here we said y is 1/5 x plus 3. Down here, we're saying y is 5x minus 15. We know those are not the same y's. The one down here is our inverse, so we need to make sure that we finish this off by replacing that y with f inverse notation. F inverse of x is equal to 5x minus 15. So let's follow those instructions to find inverses for each of the following functions. G of x is 12x cubed minus 14. We get rid of the function notation. We switch our x's and y's. X is 12y cubed minus 14, and solve for y. X plus 14 is 12y cubed. Divide by 12, so x plus 14 divided by 12 is y cubed. Now to get y by itself, we're going to take the cube root of both sides. So the cube root of x plus 14 over 12 is y. We found the inverse, so we'll go ahead and use inverse notation. G inverse of x is the cube root of x plus 14 over 12. H of x is 6 over x plus 14. again, write the function without function notation, switch your x's and y's, now it's our job to solve for y. So we multiply both sides by y plus 14. If I multiply this side by y plus 14 and this side by y plus 14, I'll have xy plus 14x equals, over here the y plus 14s get removed and we have 6. xy is 6 minus 14x, and dividing by x gives me y equals 6 minus 14x all divided by x. One last step is to use inverse notation. H inverse of x is 6 minus 14x over x. J of x is cube root of x plus 12. Rewrite without function notation. Switch the x's and y's. And now solve for y. Here y is inside that cube root, so we'll need to cube both sides in order to get it out of the radical. So x cubed is y plus 12, and we need to subtract 12 from both sides and use inverse notation. J inverse of x is x cubed minus 12. Now at times we may have a function that is not generally one-to-one, but has had a restriction imposed on its domain so that it is possible to find the inverse. Here is an example of this. Given f of x equals x squared minus 1, x is greater than or equal to 0. Find f inverse of x. If you think about this function f of x being x squared minus 1, just a quick sketch of this. This is a parabola that has been shifted down 1 unit, and it is definitely not a one-to-one function. It does not pass the horizontal line test. So when we say x is greater than or equal to 0 here, what they've done is restricted it to just the right half of that parabola. So now we can find f inverse of x. All right, so we're going to start out with f of x equals x squared minus 1. X is greater than or equal to 0. Y equals x squared minus 1, where x is greater than or equal to 0. Just getting rid of the function notation. Now we need to switch our x's and y's. Y is now x is now y, and we even do it in our restriction there. Now we solve for y. So x plus 1 is equal to y squared. Y is greater than or equal to 0. Now we take the square root. So y is equal to plus or minus the square root of x plus 1, and y is greater than or equal to 0. Now we're looking at this function. This is not a function here. Y is plus or minus something. So we put in a single x value. Let's say if we put in a 3. If we put in a 3, what comes out? We'd have square root of 4, which is 2. So y is going to be either a positive 2 or a negative 2. And that's not a function. So it's a good thing we have this restriction here. Y is greater than or equal to 0. That tells us that we want positive y's or y's that are equal to 0. So we're going to use only the positive square root. So now we have f inverse of x is equal to the positive square root of x plus 1. No need to write the positive sign out front here. We just make sure that we're using the positive square root, so it's there. And we don't need to put our restriction here because we've already applied the restriction by using only the positive square root. There are other times when you must determine a domain on which f is 1 to 1 in order to find the inverse. Here's an example of this. Let f of x equal x minus 3 quantity squared. Let's find a domain on which f is 1 to 1. If we think about this function, this is a parabola that has been shifted to the right 3 places. If we want to include as much of the range as possible, then we are going to include from 3 on. In other words, we want x minus 3 to be greater than or equal to 0, and we get x is greater than equal to 3 for us to get the right domain that's 1 to 1. So our domain is from 3 to positive infinity, or x is greater than equal to 3. Now let's find the inverse of f that's restricted to this domain. Remember, we're getting rid of the function notation. We're going to state our restriction that x must be greater than or equal to 3. Switch our x's and y's. So x is equal to y minus 3 quantity squared, where y is greater than equal to 3. Now solve for y. So I have the square root of x plus or minus equals y minus 3 after I've taken the square root of both sides. Continue to carry that restriction down with us. And I have add 3 to both sides. That gives us 3 plus or minus the square root of x equals y. Y is greater than equal to 3. Now if y is 3 plus or minus the square root of x, and we want y to be greater than or equal to 3, then we can't be using the subtract square root of x. We go ahead and apply that restriction. So y is equal to 3 plus the square root of x. This ensures that y is going to be greater than or equal to 3. We've applied the restriction, so we don't need to use that restriction written out anymore. And our last step is to go ahead and write our inverse notation. So f inverse of x is equal to 3 plus the square root of x. It's interesting to note that in our study of inversion, the idea is to exchange the inputs and outputs of a function. This makes x equal y and y equal x. Y equals x. We can do this in table form, and graph form, and in equation form now. Now what ties this all together is the observation that f and f inverse graphs are symmetric about the line y equals x. Let's look at our previous graph. We can see from our previous example there is symmetry going on here. If we draw in the line y equals x, we can see that our graph is symmetric to the line y equals x. If you fold your paper diagonally along that line, the red and blue graphs will lie on each other. So with that in mind, let's try one more thing. We stated early on in this lesson that functions must be one-to-one if they're going to have an inverse. Let's see if we can graph the inverse of a function that is not one-to-one. So, go ahead and grab a piece of paper and draw the x and y axes on it. Remember, you can pause this video at any time so you can catch up on the activities. With a pencil, draw a graph on your paper that's simple but not one-to-one. Here I've drawn the parabola y equals x squared. Now, go ahead and draw your line of symmetry, y equals x. When you're finished, fold your paper on that line. While still folded, rub the paper with the back of your nail or a coin so that the pencil graph function will transfer across that line of symmetry. Now unfold your paper, and what do you see that has transferred? The inverse function that has transferred is a graph that isn't even a function. This is the reason functions must be one-to-one in order to have an inverse. Pretty neat. Now, if we extend the concept of inversion to graphing parabolas and just accept the fact that these are not going to be functions when we're finished with the inversion process, we can graph a parabola with a horizontal axis of symmetry. So let's graph each of these vertical axis parabolas, and then we'll see what happens when we have the horizontal axis parabola after the x and y are switched. So first we start off with x squared equals 1/2 y. We might want to get that into a form more familiar to us. Let's multiply both sides by 2. So I have y equals 2x squared. This is our usual parabola that's at 0, 0 for the vertex, but this has been stretched to be twice as tall. Okay, so we have a transformation of a vertical stretch by a factor of 2. Now what happens when we switch the x and the y over here? We can go ahead and put this into a more agreeable form for us to graph. And now we have still a vertex at 0, 0. Notice this parabola was opening up. This parabola will be opening to the right. So instead of having a parabola that is twice as tall, it'll still be twice as tall, but it's laying down on its side. So in the way that we can think that this parabola was opening up towards the positive y's, this parabola is opening to the right to the positive x's. Let's try that again here where we have a shift in the vertex. So let's go ahead and get this into a more agreeable form for us. Y minus 2 equals 2 times x plus 3 quantity squared. So instead of the vertex being at 0, 0, the vertex is now at -3, positive 2 because of the shifting with x and y. Now we still have a parabola that is opening up. It's an x squared parabola, and it's twice as tall as it normally would be because of this 2. So we're going to have these points and graph as smoothly as you can. There you go. Similarly, we come over here and we'll get this into, again, a more agreeable form for us. And I see that my vertex has shifted there to a 2 and -3, and we again have a stretch of 2, except in a horizontal fashion. So we have a parabola that ends like this.